So I'll make this talk relatively short because I really want to get across a couple of points. And that is not only about speeding up your scikit-learn train time, but also how you could apply some of these principles to other machine learning workloads. And frankly, whether or not you need this to begin with. Because if something already runs fast enough, why make things more complicated or change what already works? So a little about me. I debated doing this, but I currently work in developer relations at any scale. So that primarily means for me, I write about distributed computing, do some code, those sort of things. I worked a lot with wearable data. Now, at time at Scripps, I worked a lot on Fitbit data, so seeing long-term trends in sleep and heart rate, and a lot of interesting things. Interestingly enough, especially around Christmas season, heart rate skyrockets, activity goes, down a lot. So hopefully everyone's taking care of themselves this holiday season. And I also teach machine learning at Stanford Continuing Studies. So as far as why you'd want to actually speed up scikit-learn, there's a lot of different reasons. Primarily that, I'll just introduce scikit-learn, is that it's really easy to use Python library for machine learning. However, the real problem, though, is that sometimes models can take a long time to train. So there's a couple main ways to do this. One way, and this is really simple and it sounds really obvious, you didn't come to a talk just for this, is that you should upgrade your scikit-learn. So there were recent improvements to histogram gradient boosting classifier. So essentially, if you have more efficient algorithms, you can make better use of the same hardware. So as someone mentioned earlier, it's not like you're getting more gigahertz anymore. Things are not getting smaller and smaller chip-wise. They are, but I mean, really kind of. So upgrade scikit-learn, and we'll talk about that. Another way is to look at your solver. I'll talk about that as in a bit. And there's also a lot of different hyperparameter optimization techniques. So when you have a machine learning model, modifying your hyperparameters, optimization techniques to do things more efficient than grid search, for example. And finally, even though you might have a lot of cores in your computer, you might have access to a lot of resources, oftentimes scikit-learn by default is single core. And if you're just doing your code and you're only using one core in your computer and you have 2, 4, 8, 16, or even more, you're not being very good with your resources. You can also distribute your training. So instead of doing something on one computer, you can do something across many different computers. And feel free to interrupt me if you have any questions, comments, concerns, or literally anything. So every time scikit-learn releases, and this is why I really emphasize this first, scikit-learn has pretty frequent releases that offer efficiency improvements. And it can also give you ideas of how to improve your workflow. So if you're not familiar with scikit-learn, a lot of algorithms, when they first start in scikit-learn, they don't necessarily always start with support for everything. So for example, for histogram gradient boosting classifier and regressor, they used to have support for categorical features. What this meant is they used to have to one-hot encode each column. So essentially, when training a model, when they had a categorical column, they would make one column for each category. If you had 10 categories in one column, you'd have 10 different columns. You have a lot more columns, and when you have more columns in your data, that means it takes longer to train. So for example, just by upgrading, you can take advantage of categorical features, and that can really save you a lot of time. So what we see on the right here is we have fit times for, just say, a given model, a given data set for scikit-learn. And you see on this little bar chart that you have a long fit time for one hot. And then if you just remove the categorical columns, which is just getting rid of the problem to begin with altogether, just training on less data, less columns, the fit time obviously goes down because you just have less data. And whereas if you go to ordinal support or native support, that means you still have less of fit time than one-hot encoding. Keep in mind here, though, accuracy is not always, or sorry, fit time is not always the most important thing. It's about the problem you're trying to solve. So while you do have amazing speed for just removing data, doesn't mean you have the best accuracy. And by doing things with like ordinal or native encoding, that means that you have pretty good bit time and pretty good accuracy. So the next thing I want to talk about, and this is a bit of a longer section. So many machine learning problems are really about usually, minimization of some loss function on some training set. So if you're not familiar with machine learning, you have a training set, you have a testing set. And to do this for machine learning, you want to minimize some function. And that often can take some time because you're training over a data set. So optimization functions help with the minimization process. So the idea here is what I mentioned earlier in this talk, is that when you have better algorithms, it allows you to make better use of the same hardware. So if you have a more efficient algorithm, you can produce an optimal model faster. So for example, with Scikit-Learn, there was a great talk by, I'm not going to attempt Gael's last name, but he was one of the first, he's still a core contributor to Scikit-Learn. He wasn't the creator. I think it was originally a Summer Code talk, Summer Code Project Scikit-Learn. But if you look at logistic regression, there's a lot of different solver options you have in Scikit-Learn, and then we'll go over them. So there's a full gradient approach, and in logistic regression, this is if you change your solver to liblinear. This is when you go through all your samples, all n, so basically all the rows of your data. And this is a pretty costly gradient computation, because if you go through all your data, it just is a slow process. Like anything, if you go through an entire stack of pancakes, it typically takes you longer to eat than a smaller stack, unless you're in like a food eating contest or something weird. So there's another approach, and this is a subsample approach. So basically, you have a smaller n, and it can converge. It's cheaper to compute, but sometimes it can converge much more slowly for a variety of reasons. So there's also other solvers, and there's a lot of different mathematics of why certain solvers work better in different situations, and things work depending on the problem you have, of course. But one of them that Scikit-Learn has is Saga. And I mention this because oftentimes a lot of machine learning libraries, they keep very old-fashioned defaults for a lot of parameters to make things not break. But for Saga, it's basically each iteration is cheap to compute because it's smaller number of samples, kind of like subsampling. But it converges usually relatively rapidly because of variance reduction technique. And how that works mathematically, you can read the Scikit-Learn documentation. I can send you a link. I can send you a couple of blogs about it. But I want to talk about how this works in practice, because often for machine learning, you don't necessarily need to know all the underlying mechanics of how something is implemented. So for this piece of code here, you're importing the libraries you want to use, time, make classification. This is just to make a dummy data set, train test split, logistic regression. So you have your code here, and you're just running through two different solvers. And this is for a binary classification, where they're classifying whether something is one thing or another. So just by changing the solver from liblinear to Saga, it resulted in a much smaller fit time because it's subsampling. And I should mention that with any parameters, any values for your hyperparameters, always check that they work for all use cases. So for example, liblinear is only for binary classification. So if you tried with a bunch of different values for solvers, this can make a big difference. These sort of things really only matter if you're doing something really inefficient or you have a lot of data. If you have a small piece of data or small data set, most likely, it's not going to make a huge difference because things already run so fast on their own. But a lot of this talks today is about just giving you ideas of things you can look at if things are taking a long time to train, especially if you're train things often. And as far as like, what is a solver? I don't know what a solver is. What is this parameter? When is it used for? The documentation for Scikit-Learn, I recommend for each algorithm, especially if they have a solver, is to really look at the documentation, see what's best for your use case. So if you have an unscaled data set, then you should use one solver versus another. If you have a large data set, then you probably should stick with the SOG or Saga. And then if you need to do some sort of regularization, then you need to evaluate these options over here. So my favorite part of this is to evaluate different hyperparameter optimization techniques. So this is along the lines, again, of better algorithms allow you to make better use of the same hardware that you're currently already utilizing. So we're still just using a single core here for context. Although you could use multiple cores if you change certain parameters. So for high performance on most machine learning algorithms, most people know they need to tune models hyperparameters. And hyperparameters, for those that you don't know, hyperparameters are the parameters of a model which are not updated during training. This is what you set before training. So Scikit-Learn by default contains, I misspelled something here, a couple techniques for hyperparameter tuning like grid search and random search. So let's talk about grid search, what it is. We'll talk about random search a little bit. And grid search is kind of like it sounds. If you have a entire list of 100 different items in that list, you're going to go through all 100 items. Random search is a little different, where it samples a given number of candidates from the parameter space. So if you have, let's say, 100, it's not this simple, obviously, but you sample, some sample of that 100. So you don't go through the entire list, basically, from a parameter space with a specified distribution. And so one interesting thing about this is grid search can often miss the optimal part of the important parameter. And this has to do with random search, looking over distribution and a lot of different things. But it's just something just to mention. The benefit, though, of grid search is if you have a lot of time, a lot of resources, a lot of money to blow, a hole in your pocket, oftentimes you can talk about just using grid search because it's explainable. You have a bunch of parameters. You have one hyperparameter for 3 values, another hyperparameter with 3 values, another one with 3 values. And you want to go through all the combinations of this. 3 times 3 times 3 is 27 evaluations. It's easy to explain. The problem is you're kind of at some point, especially if you have a lot of hyperparameters, a lot of values for those hyperparameters, then it can be very time-consuming, inefficient, and expensive. So for a given piece of code, I have 1, 2 hyperparameters. I'm doing a grid search on top of cross-validation. If you know what that is, that's fine. It could take like 2 minutes here. And essentially in this case, because I have 9 values here and 9 values here, I have 81 evaluations. So it's really inefficient. And that's why it took a while. So for random search, I mentioned, it's easily parallelizable, and it's pretty hard to beat in high dimensions. Grid search is also parallelizable, but some more advanced hyperparameter optimization techniques are pretty hard to parallelize. The problem, though, is in this little talk, for example, I don't have time to explain random search in a lot of detail. It's just no time. So it's less explainable, and it's less expensive than grid search, but it's still relatively expensive. But just for our case here, it's more than enough for this use case. 2 minutes, 25 seconds for grid search, and 25 seconds for random search, or 26 seconds almost. So it went through 10 configurations. One thing to note here, though, is that libraries are always improving. There's always algorithmic innovation. Like there's always something great happening. So Scikit-Learn recently added techniques for having grid search and having random search. And essentially, it's like a tournament of parameter values, and it's a great technique. So essentially, hyperparameters are evaluated with a small amount of resources at the first iteration, and things that seem to be more promising are given more resources through successive iterations. It's like a tournament. Things that do well get more money or more resources, and so on. And that's also very efficient. One thing to mention here, though, is there's a lot of different hyperparameter optimization libraries that help you use more advanced hyperparameter optimization techniques if Scikit-Learn doesn't have them. So there's Tune Sklearn that lets you use Bayesian optimization, another technique, just like grid and random search. There's early stopping. So something's not training well, it just throws it out the window, essentially, and distributed execution. So in this little GF file, something wasn't very promising. It was first started training, like one set, so just useless, and then went on to more promising candidates. So one thing to mention here is if you want to use this library, it's essentially part of the Ray project. Let me know if you want to use it. I mean, you can just go on Tune Sklearn stocks. It's very similar to Scikit-Learn. In fact, you just use most Scikit-Learn's code. It's really just a one-line replacement, and it's pretty scalable if you have a lot of parameters you want to tune. So another favorite part of the talk is about another way to speed up Scikit-Learn. So if you're just using a single core in Scikit-Learn, oftentimes you want to consider using more resources on your computer. So one way is to parallelize or distribute your training with joblib and Ray. You can use other libraries too besides Ray, like Dask and a bunch of other ones. But what you see here in the image is for A here, you have a single core. So Scikit-Learn by default just uses a single core as well as your memory. And this computer I'm giving the talk on today, I believe has 8 cores. This image only has 4. So if you want to be really efficient, you can utilize more of the cores in your computer. So most Scikit-Learn like estimators, they allow you to select how many jobs you want, so how many cores you want to use. Or you can use all the cores. If you set the parameter -1, I'll show you what that looks like. And then if you want to go from more than one computer, just like instead just the computer I'm talking on right now, if I want to go on like a bunch of different nodes, nodes could be a computer in this case, you can do distributed Scikit-Learn if you really want to. So this computer, well, this image has 4. But oftentimes you're just using 1. But the real shame in this, though, is that a lot of models for machine learning often have a lot of inbuilt parallelism potential. So for example, a random forest essentially is a bunch of decision trees that come together. They're trained slightly different data that come together to make a combined prediction. The thing is that each one of these little like paths here could be done in parallel on different cores on your computer, assuming that you have enough memory and other stuff. So that's why I recommend you check out using joblib with your Scikit-Learn. And this is really easy. So and joblib has backends like Loki, multiprocessing, Dask, and Ray. And so Loki allows you to transform your single core to multi-core. But it's not, however, for using distributed Scikit-Learn. But for most everyone here, most likely you'll be fine with using the default backend. So if you want to utilize this, It's just an added value for a given parameter. So you set -1 for n_jobs, and this will allow you to use all the cores on your computer. So I think what took like 2 minutes and 20 seconds or something before, it is now 36.5. So that sped things up quite a bit. But I want to mention that Loki can't do distributed. So for that, you need array or Dask or something similar. So the problem here, though, is that one thing to mention is distributed computing is challenging, usually, if you try to do it on your own. So this can often involve scheduling tasks across multiple machines, transferring data efficiently, and recovering from failures, because if you have a lot of different nodes or machines, chances are something will fail somewhere along the way. So a lot of distributed computing frameworks, Ray, Dask, etc., they try to make recovering from machine failures, happen pretty natively. And the image here on the right is a bunch of puppies. So on the left, you have kind of how you'd think distributed computing would go, where everything would be very organized and things would go perfectly and things would communicate well. But oftentimes puppies, they don't always have things go according to your plan. So luckily, that's where the Ray and Dask backend come in. So it can handle the details for you, keep things simple, and hopefully lead to better performance and more like the image to the left here. So I'm not going to get into so much about these graphs because I imagine I'm going to run out of time soon. But what they show is normalized speed up in terms of execution time. So basically, higher is better for the backends of Ray, multiprocessing, Loki, and Dask relative to default Loki backend. So what we see here are just different algorithms. So support vector machines with random search, grid search, and then random forests. So one thing to note here is no matter what, for whether you're training something on, this is for a distributed setting, by the way. For 1 node, 5 nodes, 10 nodes, so 1 computer, 5 computers, 10 computers, in similar terms, you're going to get the same performance for Loki as well as multiprocessing within for some reason. One thing to note here is there's going to be some variation with this, because these distributed computing libraries, they improve all the time. So for example, you're going to get very similar performance for Dask and Ray, for example, if you're training on 5 nodes versus 10 nodes. And I think at some point, if you're doing a lot of compute, Ray will definitely win out, just because of it's meant for more computation, whereas Dask is more like it was originally meant as an extension of like NumPy and Pandas. It's easier to use, better Windows support, etc. Anyway, one thing to note here is that the only ones that really mean you have better performance on more nodes are things that actually support distributed computing. So for SVM with grid search and then random forests, you should have better performance. One thing to note here is this graph is just what happens to be some older versions of Dask and Ray. If you ran this again, I'm guessing the results would be pretty similar in terms of normalized speed up. It's just that distributed computing can often be hard. If people make improvements to different software versions, oftentimes problems are fixed or there's regressions. It's just an interesting kind of field. I recommend you look at it. And if you're curious about this little benchmark, it was measured on 1, 5, and 10 M5X large cores, or M5.8X large nodes with 32 cores each. And really, Loki and multiprocessing don't really depend on how many nodes you have. So there's a lot of different reasons for this. And I should note that at some point, if you go from 5, 10 to 100 to 1,000, you'll see that you'll have some bottleneck eventually, because there's some serial part of the program. The entire program is not something you just entirely parallelize. There's at least at some point some serial part. One thing has to come after another. If you're curious what Ray is, there's I can recommend a lot of talks for you if you're curious. It's what I work on for work. I try not to make this an advertisement ever, but there's a lot of different things what Ray is, but another subject entirely. And thank you so much for your time. I know it's late. If you have questions, I have the slides here, and I'm happy to take any questions whenever.